If you work anywhere near modern tech AI, deep learning, data analysis, automation, there's one name you can't escape. Python.
It's just the constant, isn't it? I mean, for decades, every big tech shift has had its own language. The internet was, Java and JavaScript.
Right.
But the AI revolution, it is undeniably being written in Python.
And that's really the mission for this deep dive. We've pulled insights from a whole stack of sources, articles, research papers, technical analyses to figure out not just that Python is popular, but why it became the technological heart of this whole AI thing.
Yeah, we need to get past the surface level stuff.
Yep.
We're looking at its design, the ecosystem, and the hard evidence of who's actually using it.
We're even digging into the original vision of its creator, Guido van Rossum, how his philosophy kind of accidentally created the perfect sandbox for the most complex computing we're doing today.
It's a great story.
Okay, so let's unpack this. How does a scripting language created by one guy in the Netherlands back in the late 80s, mostly for readability, how does that become the code powering self-driving cars and generative AI?
We have to start right there with that philosophy.
With Guido van Rossum.
Exactly. So it starts with him and a very deliberate choice he made. He wasn't trying to build the fastest language.
Right.
Not at all. Or the one with the most features.
He wanted the most accessible.
That's it. He had this clear idea that, and I'm paraphrasing, the code must be readable, logical, and almost poetic.
That idea of poetic code is so interesting, especially when you think about what was dominant then, C++ each, Java. They were so rigid, so much boilerplate just to get a program running.
Right. And Python made these design choices that were, frankly, a little controversial then, but turned out to be perfect for AI. The most famous one is using whitespace.
Indentation.
Yeah. Instead of brackets or semicolons, Python uses indentation to show the structure of the code.
So it's not just for looks, it actually forces you to write neat code.
It's compulsory. And that one small thing, that insistence on clarity, it means a data scientist in Beijing can write a model.
And a researcher in Toronto can pick it up and immediately get the logic.
Instantly. Because the language itself forces that readability. And that laid the critical groundwork for everything that came after.
Which brings us to what might be the biggest, maybe even unintended consequence of prioritizing simplicity.
Democratization.
Exactly.
That's the key takeaway here. Our sources call it Python's softness in design. It meant you didn't need, a 4-year computer science degree to actually build something useful.
It wasn't just for the hardcore software engineers anymore.
No, it opened the door to the subject matter experts.
People who had been, walled off by the technical side of things before.
Precisely. We're talking about mathematicians, physicists, economists, biologists, people who were experts in their domain, but their main tool wasn't code.
And with Python, they could suddenly write code that worked, that scaled, and crucially, that other people in their field could actually read and understand. That single move, letting the scientists and the analysts get their hands dirty with code, that was the most important first step for the AI boom, no question.
Okay, so the door is open, the scientists are in, but they need tools, right? And this is where the magic really happens. This massive community-built ecosystem.
The foundation was there, but the real explosion in use, the velocity, came from the community building these incredible scientific libraries.
So Python is the language.
But these libraries are like the professional-grade lab equipment. They're the standardized tools everyone agrees to use.
Let's get into that tool chest, because these names are they're the infrastructure of AI. If you're dealing with data, you have to start with the numbers, the matrices.
And that's NumPy. It's totally foundational. It gives you the core array and matrix objects that almost every other scientific library is built on. It's how you crunch the numbers fast.
And then for organizing that data,
you move up to pandas. It's for higher level stuff, structuring the data, cleaning it, analyzing it. It's what data scientists use to get their information ready before the AI model ever sees it.
Got it. And what about the actual science part? The computation and, just as important, communicating the results.
Well, that's where SciPy comes in for the more advanced scientific computing optimization, linear algebra, that sort of thing. And you absolutely need visualization tools like Matplotlib and Seaborn.
Right, because if you can't see the patterns in the output, the insights are lost.
They're useless. So this whole combination of tools, it really did establish Python as the natural laboratory for AI.
Now let's hit the engine room. the deep learning frameworks that are powering this whole generative AI wave? We hear TensorFlow, PyTorch, but also Keras and JX. How do they all fit together?
Okay, so it helps to clarify the roles. TensorFlow and PyTorch are the two big rivals. They are the massive, complete ecosystems for building neural networks.
And PyTorch, that's Meta's baby, right?
Yeah, backed heavily by Meta. It's super popular in academic research because it's very flexible, very good for just trying new things out.
And Keras and JAX, where do they fit in?
So Keras isn't really a competitor to TensorFlow. It's more like a simplified interface, an API that sits on top of frameworks like TensorFlow.
Oh, so it lets you build things faster with less code.
Exactly. For prototyping, JX is different. It's Google's newer performance-focused system. It's all about high-speed accelerated math, often on, very specific hardware.
So you've got this huge interconnected web of libraries all built and shared by scientists around the world. What's the net effect of that?
It creates this incredible acceleration. I mean, we see hard proof in the academic papers.
Oh, really?
Yeah, studies consistently show that well over 70% of academic articles on machine learning,
Yeah.
the ones published by IE or on RSCA, they use Python for their experiments.
Wow, that's a huge majority. But couldn't you argue that's a bit self-fulfilling? Like, researchers use it because they know the next person will be using it too.
That's exactly the power of the network effect. That's the whole point. When a researcher publishes some new technique today,
An open source Python version of it will be out in, what, a few weeks?
if that, and everyone can then test it, build on it, iterate, that speed, that shared infrastructure, that's what keeps Python on top. No other language has that kind of immediate global support for cutting-edge science.
Okay, let's move from the science lab to the factory floor, the big tech companies. We have to talk about what makes Python so essential there, and it's this idea of it being a glue language.
This is one of its most powerful, most strategic advantages. Python is, by its nature, multilingual. It can talk to and integrate with almost every other major programming language out there.
C, C++, Rust, Java, Julia, or even really old stuff running Fortran.
It's the ultimate translator. And what that lets companies do in practice is separate the high-level workflow from the low-level super-fast execution.
Which is how it gets around its biggest weakness, the speed.
Exactly. So you write the really heavy performance-critical stuff, the algorithms that need raw speed, in a low-level language like C or C++ MIC.
But then you wrap that code in a simple, easy-to-use Python interface.
That's the core idea. One of the sources had a great analogy for it. It's like having a Ferrari, but with bicycle controls.
I love that. Incredibly fast underneath, but super easy to handle on the surface.
And that approach saves a massive amount of time and money, especially when you're trying to use code that's already been written.
Like legacy code.
Think about a bank that has decades of financial models written in high-performance C++ Manila. They don't have to rewrite millions of lines of proven code.
They just write a little Python wrapper.
And suddenly that decades-old C++ algorithm can be used in a modern data pipeline with modern visualization tools. It's incredibly efficient.
That must have created a huge domino effect. Once the big players started using it, everyone else had to follow.
It did. It becomes an industry standard overnight. Google uses Python everywhere, not just for ML. It's foundational to how TensorFlow is designed.
And Meta, of course, with PyTorch. They use it for all their internal data analysis and research.
And it's not just the old guard. OpenAI uses Python all over its experimental stack. Even a company like Tesla, which is all about hardware, they use it for computer vision, for simulation.
So the data is clear. This isn't just a trend.
No, it's an integrated standard validated by the world's toughest computing problems. And the education system backs it up. Top universities like Harvard, Stanford, Toronto. They all mandate Python for their data science programs. It's the default entry point globally.
So Python is the king. But it's not perfect. We have to do the reality check. We have to talk about its limits, especially speed and parallelism.
Right, that's the big asterisk. Python is an interpreted language. It translates code line by line as it runs, instead of compiling it all to machine code beforehand.
Which is why it's slower for certain things.
For pure sequential number crunching, yeah. And then you have the real elephant in the room for high-performance computing, the GIL, the Global Interpreter Lock.
We hear that term a lot. Can you break down what the GIL actually is and why it's a problem for modern computers?
So the Global Interpreter Lock is a mechanism in the standard Python interpreter that basically ensures only one thread can execute Python code at any one time.
And a thread is like a tiny parallel stream of instructions. So even if you have a massive multi-core computer,
A 64-core machine.
the GIL says, nope, only one stream of Python gets to run at a time.
Exactly. It's a huge bottleneck for native parallelism, which is what these massive AI models need to do their work efficiently.
So how on earth does Python stay dominant with such a glaring weakness?
Mitigation. It all comes back to that glue factor. The community just works around the GIL, those super intensive tasks like matrix multiplication and deep learning.
They just get pushed down into those specialized libraries written in C or C++ or CUD for the GPUs?
Right? They offload the hard work. The community essentially builds external tools to fix the language's native flaws, just so they can keep using that easy syntax.
And that effort to speed it up doesn't stop there, does it?
No, you have tools like Numba, Cython, and just-in-time compilers. Cython lets you write C extensions for Python. Numba and GIT can convert Python code into faster machine code right before it runs. It's this constant, dedicated effort to give the language a speed it just doesn't have on its own.
That is some serious loyalty. But looking ahead, as these AI models get exponentially larger, that need for speed is only going to get more intense.
Which leads us directly to the competition.
Yeah.
Languages like Julia and Rust are gaining ground because they target Python's weak spots.
Hmm.
Julia was built from the ground up for scientific computing. It's almost as fast as C.
And Rust is all about performance and safety.
Yeah, great for building the core infrastructure where Python is just too slow.
So what are the, say, 5 big challenges Python absolutely has to solve to stay on top of these new challengers?
Okay, first, it has to maintain relevance against them. That means the tools that accelerate Python, like JAX, they have to keep up with the native speed of Julia and Rust.
And the parallelism problem isn't going away.
That's challenge number 2. Python needs a real breakthrough there, maybe even getting rid of the GIL, to handle native parallelism better. Relying on external wrappers all the time is complicated.
What about the new types of AI? We're moving beyond just text and images now.
Right. Challenge 3 is consolidating its libraries for multimodal AI systems that handle images, text, audio all at once. The current tools need to work together more smoothly.
And what about the hardware itself, all these new AI chips?
That's number 4. Python's frameworks have to adapt fast to specialized hardware. Quantum computers, dedicated AI accelerators from Google or Intel, the libraries need to interface with them seamlessly.
And finally, a really practical one. With so many libraries, security has to be a nightmare.
That's the 5th challenge. The ecosystem is so massive. Millions of libraries depending on each other. Managing the security vulnerabilities and just ensuring long-term maintenance across that whole chain is a huge ongoing job.
So, to wrap up our deep dive, Python's success really wasn't an accident. It's this perfect storm of Guido van Rossum's philosophy of simplicity.
A powerful, self-sustaining scientific community that built the tools.
Its ability to glue everything together for high performance.
And, of course, that overwhelming corporate and academic buy-in.
Yeah.
But so what here is, I think, very human. Python didn't just speed up AI research. It democratized it.
Yeah.
By making it easier to start, it let the smartest people from all these different fields actually start building things.
Van Rossum probably never thought he was building the brain of the biggest technological revolution of our time.
No, but by giving us simple controls, he made it possible for millions of people to get behind the wheel.
So here's the final thought for you to take away from this. How will this all play out? How will the competition between Python's huge established community and the raw native speed of challengers like Julia and Rust? How will that shape the future of AI? Will the convenience we have now win out, or will the absolute need for more performance finally force a fundamental change?